Right. So, so in the previous session, we had discussed about experimental design. Uh, so, how to convert an equation into an experiment. That we have seen, like identifying variables, constants, identifying depending and independent variables, and planning an experiment, designing and developing an experiment. All these things we have seen. So now we see how to analyze things in physics. So to analyze things, the basic requirement is conservation laws. So to see, I mean, we have to see what are the things that remain constant, or the things that guide the course of an event, or the controllers of an event. Okay, so they are called conservation laws. Okay, so the first one is homogeneity in time. And whatever we deal with in physics is somewhere or somehow linked with energy. How energy converts from one form to another form, or how energy converts into mass or material, or how energy interacts with material things, is a matter of discussion everywhere. So everywhere, every physical activity is somehow linked with energy. And in the course of time, we'll see a new physical quantity. It's called action. Action is a physical quantity which has units of joule seconds. So this work and energy, all these have units of joules. So that work energy theorem in physics says that amount of work done on any system will be converted to some form of energy in the system. Let's say if you are lifting a stone and keeping it on a wall or at some height, so whatever work done on the stone will be converted into potential energy. Let's say you are pulling the pendulum to one end and leaving it, so whatever work done will be now converted to kinetic energy. So like that, every activity, whatever work done on a system will be converted to some sort of energy in the system, and these conversions is a matter of discussion. So now work has a units of joules. Work or energy both will have units of joules, and both are equivalent. That's what work energy theorem says. And then another physical quantity is power. Power is what? Work done by time. Total amount of work done. So joules per second is the units of power. Okay. So whenever we come across any physical activity, we must look for this action. So the control parameter is principle of least action. So the best choice in any activity is decided by this least action. So we have to calculate action and identify which choice has least action. Okay, so for that we have to multiply total energy into time. Okay, let's say I want to bring some 10 buckets of water to first floor upstairs. Okay, and for each bucket I am taking 1 minute. Okay, so now let's say I am taking each bucket one by one. So how long will it take? 10 minutes. And if I bring 2 buckets at a time, it takes 5 minutes. So what is the amount of action in those two activities? 1 bucket at a time, 1 minute. So 10 buckets. So 10 joule seconds. Joules multiplied by seconds. So for each action, let's say it takes 1 joule. I mean, it may take more than that, but for the time being, I'm considering like that. So what is that? So for each bucket, I'm spending 1 minute. So 10 joules multiplied by time. And if the same thing, if I take 2 buckets at a time, let's say it is 5 joule seconds. So the total amount of work done is what? Amount of work done in each stage multiplied by total amount of time spent. So in the first case, I'm spending 10 minutes. Okay, so the case 1, it is 10 joule seconds. In the second case, it is 5 joule seconds. Is the total action. So which one do you prefer? Who do you prefer? Let's say if somebody takes 10 minutes for the job and somebody else takes 5 minutes. So we prefer this one. Right? So in any activity, this principle of least action says action must be minimum. So that is the best choice. Okay. So we'll take simple examples like reflection. Let's say reflection of light. So when light reflects on a surface and reaches another point, there are infinite possibilities of paths starting from A to reach B after reflection on the mirror. Okay. So this is one possible way, this is another possible way. There are different possible ways. So which one should we choose? So which one should we choose? There are 3 possible ways for the time being. Okay, so here what are the constants? So as long as light travels in the same medium, its velocity is a constant. Because there is no change in the medium, there will not be any change in velocity. So V is constant. Okay, so we have to identify a pair of physical quantities whose units are or whose dimensions are joule seconds. Okay, so we have to identify a pair of quantities, like let's say here it is momentum and position. What are the units? So what are the units of this joule? Joule second units entante joule and energy, force into displacement. This is force into displacement into time. Mass into acceleration into displacement time. So it is ml t power minus 2 into L into T. So up to joules it is ml square t power minus 2 multiplied by T. So ml square t power minus 1 is the units of action. So check here. Momentum is mass into velocity. So it is ml t power minus 1 multiplied by L. So it is ml square t power minus 1. So if you multiply these two physical quantities, position and momentum, you will get dimensions of action. So this product can be considered as action. So now what is the condition here? Velocity is constant. So once velocity is constant, momentum remains constant. So this is constant. So least action path implies shortest distance. Right? So once momentum is constant, the control is now in position. So shortest distance becomes the best choice. Right? So that can be confirmed even here. So when the velocity is constant and there are three paths, which one should we choose? So whatever that is shortest. Right. Let's say I want to travel from A to B. There are three people traveling. Condition is the speed should remain constant. So everybody have to travel with, let's say, 30 kmph or 50 kmph. Speed should not rise or speed should not lower. Then who will reach first? Shortest is the best choice. So now we have to identify which one is the shortest path out of these three. There are three paths. 1, 2, 3. So I have to identify the shortest path out of these three. So how to get that? We have to measure the lengths of all this. Otherwise, option B, I'll take a reflection of the second half. I take a reflection of the second half. What do I get? So I'm taking a reflection of the second half. So this is the reflection of this third one. This is the reflection of the second one. And this is the reflection of the first one. So reaching A to B is equivalent to reaching A to B prime. So it is a reflection of it. So now A, B. Which one is best? Which one is shortest? So this is a straight line. So straight line is the shortest line between any 2 points. Right? So this is the point where I becomes equal to R, angle of incidence equal to angle of reflection. So that is controlled by principle of least action. So here the condition we are imposing is constant velocity. As long as light travels in the same medium, velocity remains constant. So that implies momentum remains constant. So the only free parameter that we have in hand is position. So shortest path becomes best choice in this case. Okay. So what about refraction? So when light travels from one medium to another medium. So here also we have three choices. Traveling from A to B. So here let's say this is rarer medium, this is denser medium. So light enters from a rarer medium to denser medium. So what happens? It slows down. So when it starts interacting with the material, light speed reduces. Light becomes slower. So then what happens? What is the best choice then? So we have two different media and three different paths. Here the light travels faster, here it travels slower. Okay, so one choice is travel as much as you can on the fastest route and take a straight line and a slowest route. Another possibility, take a shortest path on a fastest route and take a longer path on slower route. Another choice is in between these two. So these are the different conditions. So now, what is the control parameter? So we have to identify what is that remains constant in this activity. What is that remains constant? Velocity. In the earlier case, velocity was constant, but now that is changing. So velocity depends on what? It is a product of frequency and wavelength. So let's say this velocity 3 is now becoming 1.5. It is becoming half of the original after entering the new medium. So which one should I reduce? Either frequency or wavelength. I have to reduce any one of these two or both. I have three possibilities. Either I have to reduce frequency and keep wavelength constant, or I have to reduce wavelength and keep frequency constant, or I have to reduce both. What should I choose? Frequency remains constant. Why? Okay, so we have to see what happens if I change frequency. So what is frequency? Number of oscillations per second. Let's say on the top side, the wave is making 10 oscillations per second. And the bottom side now becomes 5 oscillations per second. Right? So what happens? So on the top side, the wave is making 10 oscillations per second. Here it is only 5. So in the meantime, a wave gets disconnected if frequency changes. Right? So we cannot alter frequency when light crosses a boundary. So at least at the boundary we should ensure the frequency should remain constant, so that the wave remains connected even after how many ever oscillations it takes. So what happens? Frequency is constant. So you have to reduce the wavelength. So lambda now becomes lambda by 2. Okay, so that is why refractive index is given by, let's say if it is C by V, it becomes nu lambda 1 by nu lambda 2. Frequency is constant during refraction. So now we have to see this condition. We have to calculate action. So we have to identify a physical quantity where frequency is a constant. A pair of quantities that contains frequency as one of the parameters. So we have to identify a conjugate pair that produces action. So here position and momentum are the conjugate pair that is generating action. In this case, we have to identify a pair that includes frequency. So if you see energy and time, product of energy and time as the dimensions of units of joule seconds. So this is action, and we can write energy as h nu. H is Planck's constant, nu is frequency. So here this is a constant. This is already a constant. So what are we left with? Time. So least time is the least action path. Okay. So how to justify that? Let's say there are the 3 different paths. One is with full of traffic, another is with moderate traffic, another is with partially traffic, and other half is with more traffic. Right? We are traveling from one medium to another medium. and one part of the journey there is less traffic, and the second half of the journey has more traffic. So which one should we choose? I mean, who will be the winner? So now shortest path may not be always a good choice. So even here also we can take the shortest path, but that may not be a best choice. Either best possibility might be this one, where we're traveling least distance in a roughest road, right? So the best choice is whoever comes first is the best, right? Whatever way you take, you should reach first. So that is what least time. So if you calculate the time of travel between those 2 points from A to B, the best choice, I mean this you can find in your book. So you can see the derivation in H.C. Verma Concepts of Physics. Okay, so if you choose the condition for shortest time, like dou s by dou t equal to 0, s is the displacement from A to B. So let's say it is s is equal to AO plus OB, the distance. And if you continue the derivation, you'll be left with the best choice will be where C by V is equal to sin I by sin R, where the velocity ratios is equal to angle of incidence and angle of refraction ratio, sine of the angle of incidence and angle of refraction ratio. So this you will arrive at that condition. So the shortest time path is now coincides with Snell's law. Okay. So that is the situation. So that is how this principle of least action controls every physical activity. And the major parameter in this is the energy. So everywhere energy is being converted from one form to another form in every activity, and the amount of time it takes is a matter of discussion, and that is what this least action principle controls. But wherever we come across, we have to deal with energy. So this conservation laws also deals with energy. How energy varies with time or with space is a matter of discussion here. So the first conservation law deals with homogeneity in time. So it implies dou E by dou T is equal to 0. So the energy remains constant as a function of time. So you can write energy in various forms. One possibility is let's say force into displacement. Force into displacement, or another possibility P square by 2m, kinetic energy. So if I write this energy as force into displacement, further I can write force as a negative gradient of potential that we have seen already. If the force is conservative force, the force is conservative force, this can be written as a negative gradient of potential into displacement. Okay. These details is not a matter of discussion now. Anyway, so this dou E by dou t, if dou E by dou t is 0, is constant in time. So whatever energy you take, it is constant in time. So that is homogeneity in time. Another one is homogeneity in space. So as a function of time, here you are studying the variations in energy, and it is constant on whatever time you are recording the data. So at 1 second, 10 seconds, 1 hour, 1 day, if the energy remains constant, the statement is energy is a constant on time. Homogeneity in space. So here dou E by dou x is 0 as a function of position. So at various locations in space, energy is constant. So we have to write energy in the form of that includes the term of position, so that we can take a derivative on that. Okay. So what happens? So I can write it as a positive displacement here. So, F comes outside. So force is 0. That means what? dP by dt is 0. Otherwise, P is constant in time. Okay. So homogeneity in space. So at various locations in space, if energy remains constant, what happens? Force becomes 0. Okay, at various locations, if energy is a constant, force becomes 0. So what is the control parameter for force? Who generates force? Difference in potentials. So if at this point and this point, if there is a potential difference, energy difference, then only there will be a force from high potential to low potential. Okay. Otherwise, if every location in space has the same energy, what happens? Force becomes 0. Momentum is a constant of motion. So momentum remains constant as a function of time. Okay, so this is a second conservation law. Third one is isotropy in space. Isotropy in space. So isotropy means as a function of theta. So dou E by dou theta is 0. So at from a single point in various directions around it, energy is constant. Just like in a hydrogen atom. At a fixed distance r from the nucleus, and the force experienced by the particle is constant. The energy of the electron around the nucleus is constant at a particular distance. So whatever may be the direction, if the distance is fixed, energy is constant. So that kind of situation. It is called isotropy. Iso means similar in space. So around a point, the energy is constant at a fixed distance in space. So then what happens? So we have to convert this into some function of time. So if energy is isotropic in space, what is that remains constant in time? That is what we need to identify. Okay, so here also if energy is constant in time, this is clear. If energy is constant in space, momentum remains constant. Here, energy is isotropic. Then what happens? So we have to develop some function of time. So I write it as dou by dou t dou E by dou theta by dou t. Okay, so that dou theta by dou t is what? Dou omega. So I had to write energy in terms of omega. Okay, so what do we have? Ek kinetic energy is p square by 2m. So if you write it in terms of rotatory motion, angular terms, p square r square by 2m r square. L square by 2l. Otherwise, I can write it as half I omega square. How can I write it? P square r square. So it is m square v square r square by 2m r square. I is mr square. So m cancels. Half mr square. I write it as half I. What is that remains? V square by r square. Omega is v by r. So in total it is half I omega square. So this is a kinetic energy in circular motion. Half I omega square. In linear motion it is half mv square. So that can be replaced with half I omega square. So now we have to take dou E by dou omega. So what do we get? Dou by dou t of dou half I omega square by dou omega. So what do I get? Dou by dou t of half I omega square now becomes 2 omega I omega. We will be left with I omega. Omega square derivative 2 omega, half gets cancelled, I omega. So what is I omega? It is angular momentum. So dou L by dou t is 0 or L is constant in time. So when there is an isotropy in space, that means if the particle experiences equal amount of force at a fixed distance from a point, then angular momentum remains constant in time. So everywhere we have to see the energy conversions as a function of time. That is what this action says, and least action controls the physical activities. So every time we have to see how the energy varies as a function of time. Energy variations as a function of time, and calculate action, decide the least action path. That is a control parameter for every activity in nature. So we have to see how energy varies as a function of time and as a function of space. And we have to see what is that remains constant as a function of time again, because ultimate aim is to study the system as a function of time. So even if the energy is homogeneous in space, what is that remains constant as a function of time in this case? So if the energy is constant in space, momentum remains constant in time. if the energy is isotropic in space, angular momentum is constant in time. So that is how the rules are developed. So we have to see in every physical activity what type of symmetry is there. Is the energy is constant in time? Is the energy is constant in space? Is the energy is isotropic in space? Well, these are the general three possibilities. So based on the situation in the given system, we have to apply the corresponding conservation laws. Conservation of angular momentum, conservation of linear momentum, conservation of energy, total energy. So these are the guiding principles for every activity in nature. These are the three conservation laws and action. So we must ensure these things while studying any process or any phenomena in physics. The rule applies even for thermodynamics, mechanics, electromagnetic theory. Wherever you come across energy, you have to see these conservation laws and see the least action path. That is a guiding principle for every physical activity in nature. Done.